we'd sort of sketch the definition of Donaldson invariance. So the upshot was that if we took this principal, say, PUN bundle over a 4-manifold, then the Donaldson invariants eventually give us a function on the symmetric algebra of H naught plus H2. A whole bunch of copies of these. There are, if it's SUN, PUN, then there are n minus 1 copies of this tensor product, and it maps to Q. And these, remember, are defined by these guys. Generators of the symmetric algebra give us generators of the cohomology of the space of connections. And then we evaluate those cohomology classes on the appropriate moduli space of connections. So formally, this guy on. So let's just stick to the case where n is 2. So there's only one of these guys. So this guy would be evaluated on some generators. So a bunch of points. So these are points in X and a bunch of surfaces, sigma 1 through sigma L. That's when you get these mu classes. Evaluate on the fundamental class of the moduli space on P and X for some metric G. And a little more precisely, we're supposed to think of each of these guys. So the points give us codimension 4 subvarieties of the moduli space. The surfaces give us codimension 2 subvarieties. And I mean, we can think of them as giving us loci in the space of connections, but then I intersect that with the moduli space, and we've arranged this so that the intersection is points. So this is sort of signed. Kind of points in these guys. Okay? So much like the definition of the Gromov invariance. Now, what do we know about these things? So, we'll stick to the case n equals 2 for the moment. So a nice important feature of these things is that if I have a 4-manifold B plus is bigger than 1, and it's a theorem of Munoz that that there exists an n which depends on x, so that this Donaldson function of p and x, when I evaluate it on x squared minus 4 to the n times anything, it gives me 0. Okay, so this is an interesting number to understand about a 4-manifold, and the kind of conjecture question is that actually n equals 1 for all 4 manifolds with B plus bigger than 1. That's the simple type conjecture. Conjecture came before the theorem. Yeah. I'm sorry. Different n, though. Let's call this D. But this is for n equals 2. That's right. And there's a more complicated, So there's a similar, well, it's a conjecture for higher n, but there's a similar result that should hold for all n. But then there'll be some interesting, here, a point gives us a 4-dimensional cohomology class. In a higher rank, a point will give us n minus 1 cohomology classes, and there's some interesting polynomial generalizing this so that some power of it should kill all of the invariants. Sorry, D is 1. Yeah, that's right. And so we know this holds for many, it holds for all examples that we know how to compute, essentially. But assuming this, it makes sense to simplify the story, and let's make a generating function D, which is just going to be first formal, but then we'll say it actually makes sense, a function on the homology, D of x and p, and D of x and p on class H is the evaluation of 1 plus, say, x squared over 2 e to the h. So thinking of e to the h as that's a formal power series in the symmetric algebra. H is just an H2, right? So if we look at this guy, then a theorem that Peter and I proved 100 years ago says that there exists cohomology classes they're actually integral cohomology classes. So let's assume B1 is 0 for the moment, and corresponding rational numbers, so that actually this guy, D of x and p of h is e to the h dot h over 2 plus the sum I equals 1 to m alpha 1 e to the k alpha I e to the ki dot h. So part of the content of the theorem is that this formal expression actually is a finite convergent series, and in fact it's equal to this guy. These ki are congruent to W2 of the tangent bundle mod 2. And hey, new haircut. And furthermore, for all sigma embedded in X, smooth oriented with sigma dot sigma greater than 0, we have the Euler characteristic plus the self-intersection number is less than ki dot sigma. Okay, so this is sort of the theorem kind of pre, maybe primed the existence of the Seiberg-Witten invariants, where you reinterpret get some PD for spin C structure. So Seiberg-Witten invariants eventually are functions on spin C structures to the integers. A spin C structure gives rise to a pair of spin bundles and Clifford multiplication, but in particular C1 of W plus. So these are C2 bundles. C1 of W plus is congruent to W2 on the tangent bundle in mod 2 homology. And the conjecture of Witten and the theorem of Fian and Linnes in some generality tells us that in fact that the that sum there is really there's still the H dot H, but it's really a sum of the Seiberg-Witten invariant sum over spin C structures. C1 spin C structures. That's an S E to the C1 of W plus on H, and there's some sign that you have to be a little bit careful with, but so that's what we know about the Donaldson invariants. I mean, one of the things we know. And what else? Yeah. So So I thought that, well, yeah, in 10 more lectures I could do something interesting, but, What? So I thought, okay, we've got these Donaldson invariants. The definition's quite complicated, I will admit, but I mean, yeah, so let me start to go, how do we compute these guys? So the kind of original way to do it is, so we want to need to understand these ASD moduli spaces. And so if X, our form manifold, underlies a Kähler surface, or say, it's a projective complex surface, then there's a theorem of Donaldson and independently Uhlenbeck and Yau, which tells you that that we can identify the moduli space in some PUN bundle on X for a Kähler metric. You can identify that with stable holomorphic vector bundles on X viewed as a projective variety. And while, you know, when you first run into these things, they seem perhaps worse than these things. If you hang around algebraic geometers for too long, you realize you can do lots of computations. It's just often a matter of patience. Greetings. Oh, dear. Also haircut. Same barber?
Mine was very cheap. I did myself.
That,
Zoltan didn't do mine.
okay. That's probably best. Okay. But, of course, in the long run, we want to develop cut and paste tools. And that's where Floer homology comes in. So let me try and motivate what we're going to do here. So imagine we have four manifold split into pieces, and we're looking at solutions to this PD, and we're going to try and imagine what happens when we just stretch along this three manifold. Well, you know, we have some solutions here, and they will, as we stretch, if it's a topological, there's some, you know, that as we stretch, the solutions here they'll always be solutions, and they'll limit to some solutions that have some kind of, you know, they may leave lumps of energy on. You should think of the limiting picture as being, you know, we have X minus with a kind of infinite cylindrical end, and then maybe many copies of a cylinder, and then a copy of X plus with a cylindrical end. And as we limit, we're going to get solutions on X minus with a cylindrical end, maybe a bunch of solutions on here. There might also be some bubbles here or there. The bubbles might have multiplicity, kind of complicated, but, you know, well, we just have to learn how to deal with that. But the kind of fundamental observation to make is, first observation to make is to understand the ASD equations on a cylinder. And in particular, so let's write so I have a connection on the cylinder. One thing we can always do if we have a connection on a product is we can do a gauge transformation so that the derivative in the t direction is just the product. So we can assume that our connection A is really a one-parameter family BT of connections on Y. But then the curvature of A, what does it look like? Well, there's going to be a term which comes from differentiating the connection in the t direction, and that'll give us a dt times dB dt, and then it'll just be the three-dimensional. So let me put a 4 here to indicate that here I'm thinking of the curvature of the connection on r times y, and here that's the connection, curvature of the connection bt on y at time t. So that's what the curvature looks like. And if I give this guy assume that our orthonormal frame looks like this, then you notice that the Hodge star of dt wedge ei is, well, let's say, Hodge star of dt wedge e1. Yeah, let's say it this way. The four-dimensional Hodge star of dt wedge ei is just the three-dimensional Hodge star of ei, and also the Hodge star of ei, four-dimensional Hodge star of ei wedge ej is dt wedge the three-dimensional Hodge star of ei wedge ej. Okay, so you can check that there are no signs in these, turns out. So so this guy is ASD if and only if dB dt plus star 3 of FB equals 0. So the anti-self dual equation on a cylinder becomes something that looks like a gradient flow equation. And in fact, what else I would say? Yeah. So if so I've got my principal bundle here, and let's say it's the pullback of some principal bundle Q over Y by the projection. We'd like to interpret this as a gradient flow, so we need the function. So there's the well, yeah, how to say this? So yeah. So yeah. So on space of connections in Q is an affine space for the space of one forms, and we can define an inner product on one forms using the Hodge star to be A wedge star B. And then what we see is that this guy is corresponds to a one form under this pairing. So there's a canonical one form on the space of connections. Let me call it B. The value of the one form is just the pairing of the curvature with B. And so this is, here again, B's in the tangent space. So this assigns to every tangent vector a number, and this is a closed gauge invariant one form. And you should think of this as being the, this is the, as an analog of this in symplectic Floer homology, which is the differential of the area functional, the symplectic action functional rather. Yeah, what do I say? So, so this is sort of formally closed. It has a nice primitive, which you can get by integrating this expression, or a nice way to think about it is the following. So we want, we've got this one form. We want a primitive for it. We want to get a function on connections, not just on the tangent space. So if I have a connection on my 3-manifold, suppose that 3-manifold is the boundary of a 4-manifold and the connection extends. Then there's a natural function to write down. I can look at the Chern-Bay form, for A. Look at the Chern-Bay form for A, and then that, so you notice that this the value of this expression, well, it's almost independent of the choice of A, but it only depends on the extension up to what? Well, it depends on the extension up to the value of, of this guy on, let me call this x minus on x, where x is closed. Right, but this is a topological invariant, so this is in some, depending on exactly which principle, what kind of principal bundles we're looking at, this is in some some rational number times, well, there's some, let's say, pi squared times a rational number times z sitting inside R. So, so this value of this guy, that's the Chern-Simons of B, and it's well defined up in R mod whatever this unpleasant number is, right? And it turns out that that's the primitive of, that's a primitive of this one form. else do I want to say about that? Maybe nothing. Yeah. So you can compute it more explicitly. Let's not do that for today. So yeah. So so the Instanton Floer homology is a Morse homology of Chern-Simons on space of connections in Q mod gauge transformations in Q value in R mod Z, and this is, I should say, when it is defined. When is it defined? So there's some problems because, so problems with the definition. Or let's say problems with making it well-defined. There's sort of the usual problems. There's the spectral flow issue. So do you or don't you need to use a Novikov ring? There's bubbling issues. But it turns out that while these are new and sort of relatively speaking in the context of Morse theory and infinite dimensionals, these were new issues when Floer ran into them. They're surmountable. The more unpleasant thing is problems with G not acting freely on the space of connections. So that so spectral flow and bubbling. Yeah. Those are, and then there's this issue, which is somehow actually worse. Or anyway. But so sometimes we can avoid star. So let's say we have P over Y is admissible if, well, there are no reducible flat connections on Y. And this depends, can depend on a choice of precisely what gauge group you use. So let me give you an example of an admissible Y. So let's take the 3 torus, and we want a principal SO3 bundle on it, but let's think of the corresponding rank 3 real vector bundle. Then, there's a kind of interesting guy you can write down. I think I mentioned it before, but what we can do is let's first start off with T2 and pick 3 non-trivial line bundles on it. Distinct 3. So let's call them C1, C2, and C3. So these are non-orientable line bundles. But if you look at their sum, that's going to be orientable, right? Because the, in the W1, these guys have in terms of some generators X and Y, these guys, the total Stiefel-Whitney class of this guy is 1 plus X, 1 plus Y, and then 1 plus XY. So, W of total Stiefel-Whitney class of C is just 1 plus XY. So it's a non-trivial, it's orientable, W1 is 0, and W2 is non-zero. Right? So then I'm going to look at this guy is the bundle that I want on the 3 torus is, say, C times S1 over T2 times S1. So just the pullback of this guy to something. Now, this guy, as such, has a flat connection, because any real line bundle has a trivial flat connection. This guy has a flat connection. And you notice that it's holonomy. The holonomy around 3 the holonomy around, of this connection around the 3 loops that are these generators. Holonomy, the first one might be this, second one, the diagonal guy might be that, and then the other guy might be that. So in particular, the holonomy group of this guy is this Klein-4 group inside SO3. And so it's still a reducible connection, all right? Because this group commutes with itself, so these guys actually give you, thinking of these matrices as you can, as also automorphisms of this bundle, right? Namely, you think of, if I have one of those matrices, I can also think of those matrices as automorphisms, as X by -1 on the fibers of this guy, -1 on this guy, and +1 on that guy. That's an orientation preserving automorphism of the bundle, which preserves the connection. It preserves that splitting, right? Now, well, I should think a little bit more carefully about what gauge group I want to use here. So that, important. So the most obvious choice is just, I'm going to take the full SO3 automorphism group, so sections of the corresponding add P bundle. But there's another slightly more clever thing. Remember, so this is P crossover SO3 with SO3, where it's acting by the adjoint representation here. But there's a slightly more clever thing that I could do and look at P crossover SO3. SO3 also acts on SU2 by conjugation. Right? Namely, when SU2 acts on itself by conjugation, -1 acts trivially. So it descends to an action of SO3. And I could look at a new gauge group, which is sections of this add P tilde bundle over the 3 torus, or in general. Now, the observation is that these non-trivial automorphisms of my flat connection, let me, so this implies a connection, let's call it gamma flat. These guys don't lift to add P tilde. And in fact, there's a nice way to kind of package all of this. So do not lift. So there's one slight disadvantage to add P tilde. It's got plus or minus the identity sitting in it. Right. If an obvious section of the bundle add P tilde is just a section that assigns -1 to every point. Right? Because remember, these are maps from this total space to the group that commute with conjugation. But if I take something in the center, it commutes. So these guys are in here. Now, this then, composing with the covering projection, that maps to the SO3 gauge transformations of P. And you can measure whether they lift or not. There's a map from the components of this guy to H1 of whatever, R3 manifold with Z2 coefficients. And in fact, what you can check for the non-trivial automorphisms, they map to non-zero elements here. And you can kind of see this map in a nice way of understanding this guy. If I have a U in here, then I can form the mapping torus bundle. Look at I times P, and I identify 0P with 1 U of P. That's a bundle over S1 times Y, right? But this is an SO3 bundle over S1 times Y. It has a second Stiefel-Whitney class. Right? And that second Stiefel-Whitney collapse lives well in H2 of S1 times y with Z2 coefficients, which is isomorphic to H1 of y with Z2 coefficients plus H2 of y with Z2 coefficients. The H2 of y bit, well, that's just the second Stiefel-Whitney class of the bundle P to begin with. And the component here is the obstruction to be able to lift it back. So anyway, so, at the cost of a little more topology, if we instead, say in the context we're thinking about SO3 bundles, we're just going to mod them out by this smaller gauge group, mod the space of connections out. And then, well, we have at least one admissible guy. And then if we have any three manifold, any y, well, then let's connect summit with T3. In fact, any three manifold with any SO3 bundle, we're going to connect this guy with T3 and kind of induce with that connect sum the connect sum with this guy one of these guys that we constructed, and they're going to use this G tilde gauge group. Now, you notice what happens on the level of representations of the fundamental group. So if I have, so I should say, it's an exercise to see that actually this was the only guy, the only flat connection on this bundle. Okay. Now, so there's a unique irreducible flat connection. At least it's honestly irreducible when I use this slightly smaller gauge group. And then, well, if I have, if I have a representation of the fundamental group of this guy, and I'm trying to test it's irreducible or not, I can just, if it's irreducible on part of the three manifold, it's got to be irreducible everywhere. Irreducibility infects things, right? So no gauge transformation that fixes no non-trivial gauge transformation that fixes the connection here. There'll be no non-trivial connection on the gauge transformation on the whole thing. So in this way, you can some kind of Instanton Floer homology is easily defined for all admissible three manifolds. Easily is, of course, a misnomer, but it sort of, the only technicalities are bubbling and spectral flow issues, and we know how to do that. But okay, and what else I want to say? And then there's this trick. You can promote this to, arbitrary three manifolds equipped with the base point. And then using this connect sum construction. So you can kind of compare that to the story with HF hat, which is sort of much easier to deal with, and involves picking a base point. There's an analog in the Instanton story. So I should say there's also there's a lot of work about dealing directly with general three manifolds. There's older work of Austin Brahm, Donaldson, and much more recent work of Mike Eismeier Miller, and then work with Daemi and Daemi Scaduto, which goes a long way to kind of just dealing directly with the technical problems when you have reducibles. The sort of these original versions, it wasn't quite clear that you got a functor, and then I think, at least for rational homology spheres, this work eventually does deal with that. So let's see. Any questions about this very quick and vague stuff?
What are the main shortcomings of the Austin Brahm?
Main shortcomings. I mean, what? It's beautiful. No, it's like there's sort of a lot of work, and then maybe there should be more. I mean, that, and I mean, also they don't claim to, what you want. I mean, yeah, what's the goal? The goal should be like, I mean, now we understand much better than they did then what the goal is, right? And the goal is to get, we want to get a package of actually 3 Floer theories, kind of, if you will, an I plus, an I minus, and an I infinity. These are kind of, well, yeah. They're almost functors on a cobordism category, but they're not quite in ways that prevent them from satisfying the axioms of TQFTs in important ways. So, I plus maybe allows only one non-empty, or one a connected non-empty. I don't know if the empty set is connected. I guess it's connected. 3-manifold as input, but arbitrary output, including empty. Right? I minus has the opposite property. It allows arbitrary input, but the output is just allowed to be a connected non-empty 3-manifold. Right? So it's not really a functor because the objects in the domain and range aren't the same thing, right? I infinity it doesn't care. Okay, so I minus is reversed. I infinity is really an honest functor on kind of what people might call Cobb 3.1. I mean, you need to decorate them with bundles, but I'm not going to. So the content of this, well, there should be a well-defined map for cobordisms, and also including elements of the symmetric algebra of the cobordism. But what do I say? Yeah. So the thing that, I mean, yeah. So I think in what Austin and Brahm are able to prove is that it's not actually an invariant of even a 3-manifold. It's an invariant of a 3-manifold together with, so say a rational homology sphere, together with a perturbation that makes sure that the critical points have are non-degenerate, but they could have stabilizer. But they don't know that it's independent of the choice of perturbation except in some restricted setting. So whereas the Eismeier-Miller stuff and with Daemi, at least for rational homology spheres, gets that much going. So it's still not quite what you want. I should say maybe one more thing from the past, but which now has much better proofs. There are surgery triangles for the, let's call it PU2 Floer homology. That's Floer's original work, and then there's some better proofs by Peter and myself, Chris Scaduto. And they're it's an interesting story for higher rank, which is not quite done in general yet, but for PUN, there are surgery polygons for PUN. That's due to color Daemi and Scaduto. That's quite pretty. So for SU2, there's a surgery triangle. For SU3, there's a kind of surgery square. SU4, there's a surgery pentagon, etc. And anyway, that's, I mean. Can you remind us what square means? It means that if you so yeah.
Anyone is a net two. Anyone is a two-step mapping component of the other two. Is that?
Yeah, that's right. That's what I'm. Etc. And it sort of, I mean, there are, the yeah, that's what it means.
Is that some quadruple something as massive product as one? Is it the way of thinking about it?
I mean, that's the way they prove it. Yeah. And then they're, yeah.
But it's
I mean, but it's, so,
not a long exact sequence.
what?
No,
No?
no, it's more than a long.
It's more than a long exact sequence.
The spectral sequence, like.
Yeah, you need three, yeah, like, if you want to know the SU3 homology, you need to know the chains for 3 of them, and then a mapping cone and another mapping cone. So there's, there'll be, there's a chain complex that kind of looks like that, with the, the differentials go. That's right.
Sounds like a potential generalist problem.
What?
Sounds like a potential generalist problem.
But it's over, right?
Yeah, it's over.
Sorry.
It's
Yeah.
always fixed.
Yeah. Anyway, that. Okay, I think that's enough. That's it.